Today's recitation here, we're dealing with projections. Basically, this is just ways of viewing things in 3D. And cyclohexane's a really good way to go. For one, it sets you up for some sugar stuff going into biochemistry. There's some, it actually really helps with the DNA as well, and some of the projections there. Doesn't help so much with proteins, but again, if you're starting to deal with big macromolecules, particularly biological ones, this is going to start becoming a much bigger deal. Now, I want to reiterate from Dr. Vickery's email, I've got a lot of people asking for individual meetings. I don't view that as fair to other students, because one-on-one time, it detracts from the possibility of other students. If you come to my office hours, and again, it's going to be 8 to 10, 3 to 5 on Friday on non-exam weeks. On weeks where I have time, I want to move my office hours before the night before the exam. Okay, so I'm trying to do the best I can. There's times I can't do it. Just I'm locked in lab and there's things I'm doing. If you come to my office hours and I deem that we need more time to discuss it, I will usually do it via email, or that's when I'll do a one-on-one meeting. But again, I'm not getting that many people in my office hours, but they want to schedule me at like a very convenient time for them. I have to do it during my office hours. It's just a matter of timing. So, and being fair to other students. So with that in mind, a lot of stuff today, and I'm going to stop sharing for just a second, is going to be learning how to draw this stuff. Let's see if we can angle the camera here. This is going to be a little bit of fun here. Can you guys see what's on the marker board online there? A little bit of blue. Okay, cool. So you got to learn how to draw this stuff and well. And students often forget that you need to be able to draw this coming into the exam. So what ends up happening is students forget to do it, they forget to practice it, and then they can't draw cyclohexanes on the exam, and they spend 30 minutes on one problem and then they go. Okay, so make sure you practice doing this. What I would recommend here is in X here, those two lines are parallel. Y here, those lines are parallel. And Z here, those lines are parallel. A good way to start is with the middle carbons. And if you want the down vertice being over here, you make this line shorter. If you want the up vertice over here, you make this line a little bit longer. Now, I'm not a big artist guy, so you can see these are not exactly parallel, but I'm doing the best I can with the brain that I got. Likewise, if you want the down vertice down here, you got to make that line longer, and then this line longer for the up vertice. You want to practice this to a point where you can just whip them out like this. Oh, that was terrible. It's talking and drawing at the same time, and I have issues. Practice this. Again, practice this. If you're having issues with it, just sit there for 30 minutes and do it. It's like trying to learn how to draw letters. Like, you got to be able to do this. So, wanted to iterate that before we went into the recitation for today. So, a lot of today here is going to be based on projections. So I put up a bond line formula. Bond line formula would also be wedge dashes like this. Last week, I made some mistakes. I said that this was a Hayworth projection, the one I'm drawing now. This is not a Hayworth projection. I'm sorry. It's this one over here. Okay. Now, this one happens to be shown with wedges and dashes. Dr. Vickery was showing this as straight lines. And oftentimes, it's straight up or down like this. They were trying to be a little bit more, let's say, artistic. But this is the way to show those Hayworth projections. And that's going to come into with cis-trans. When we start talking about EZ, there was a question yesterday that hinted at EZ, which is another one when you're dealing with three or more substituents. And eventually we're going to be moving into chirality. How do we name things that have 4 different substituents coming off the same carbon, but are have different orientation, much like your hands have the same digits? Yes. What's that? Oh gosh, I forgot to share, didn't I? Sorry. Thank you. I think every lecturer does that at least once a week. It's I know there's memes about it, but like it's a lot easier than you think to do it. All right, so we're talking about these projections here. So again, these are just different ways of looking at it. Depends on what research you're doing, what kind of talk you're having. Fisher projections are really great for sugar chemistry because it allows us to isolate certain reactions that occur. For you guys, they are a pain and a half. Okay, and that's gonna be next week. We'll deal with that at its own time. That's gonna be building into, again, the chirality. We're gonna start talking about R and S, richtig or sinister, those of you that know your German. And again, it has to do with the right left of your hand is the way to think of it. You have the same digits, but it's not, you can't overlap them. And it actually causes different chemistry. And I believe you're coming up to that in a lab here, I think lab 8 with polarimetry. I don't know if anyone's read ahead. Sure, why not? All right, so I have a list of questions here. They're coming from problem set 5. And we're gonna be bouncing around between Newman projections. I didn't draw a Newman projection here. It would get pretty complicated pretty quick for the sugar, so I was dodging it. I'm actually gonna start with problem 3 here. If this problem is not on the exam, I will be actually pretty shocked. Okay. This problem requires you to be able to draw the Newman projections. It requires you to understand the strain that we were just talking about up there on the marker board. Don't worry, we'll cover that as soon as we get going here. A good way to start these kind of problems is to just draw this Newman projection first. Now you're looking down the AB here. Now in my mind's eye, I'm drawing again that line that I keep talking about. So if things go above that line, that's not very visible. Let me see if I can make that better. There we go. So if things go above that line, if you will, so up and to the left, it's going to be above a horizontal line here. If it's a straight line, that means it's in the plane of the paper. So it's going to be on this vertical line. And then you have to keep in mind your point of view, right? It's coming up towards your right here. It's going to be wedges come out towards your right if we're looking down this way. And then dashes coming out towards your left. So in this case here, we're going to put the pH right in front. I'm going to put the methyl group right there. And then H's. What does pH stand for? What? No. Well, right. pH is the negative log of hydrogen concentration. But in this case here, what does pH mean? It's a phenyl group. Phenyl group, yeah. It's a benzene ring. Okay. So there's a lot of times we'll use shorthands like Me, pH, Et, and it confuses students. Just keep that in mind. Pretty bulky group. And you need to place it on here. Usually you want to start with either the sin or the anti? What do I mean by sin here? Yeah, they're eclipsed, right? So you want to have it be sin is the highest energy where your largest substituents are eclipsing one another. Now I put it over here at 0 degrees. What is this chart? What is this XY table or graph? What are my axes here? Yes. What do you mean by energy levels? Like how much strain is being caused by that information. Right. So think of this like gravity. The higher up you are in the chart, the higher you're up in the building. And so the more energy you have if you happen to jump off the building. That was morbid. Sorry, it's early. So what we're going to do here is we're going to rotate. Now the reaction coordinate, what that means is you can either go left, you can go right on this x-axis. It's just a point of view. Now you're going to either rotate the front or the back. You're either rotate the front or the back carbon. You're going to rotate it either clockwise or counterclockwise. And you're going to keep doing it that way. Now, the way students mess up this problem is that either they start switching up the clockwise and counterclockwise, or they start switching up which carbon they're going to do. Whatever you do, keep it consistent. I have my way. I like rotating the front carbon. That doesn't mean you have to. So I'm keeping the back carbon locked in place. But I've rotated this 60 degrees such that the phenyl here has moved clockwise. What's this orientation called? Oh, staggered too, yeah. This is more stable. Now, again, the reason we're seeing this instability in the sin is we're seeing a lot of steric strain. Things are bumping up against each other, which causes torsional strain around that alpha and beta carbon that we were looking down on. So now if we rotate it again, trust me, drawing out these templates can be a chore and a half. That's why I'm copy pasting a lot. What's this called? We're going to do one more rotation here. Once again, I did 60 degrees. And what's this one called? Anti-periplanar. I'm going to call it anti here. I don't know how she's going to ask this question. It could be a, line them up A, B, C, D, E in order. It could be you have to draw out the whole thing, including the XY chart. This will be on the exam. I've never seen it not be on the exam. So be able to rotate that molecule and place it on there. One of the big stepping stones is where to start. And again, I would either start with the fully eclipsed with the sin, or with the most stable with the anti, and then move forward. Any questions on that? Yes. So we start with the anti, like I started with the anti graph set up like as the nearest to like y-axis is going to be the lowest down. Yeah, you would start here with this. So her question is, if I started on the anti, what would happen? This whole curve would just get shifted over to the left, and you'd start here. So I mean, we can keep filling that in, right? I didn't finish all the confirmations here.
But like with the graphic, it's like it's sort of flipped upside down. You know what I mean?
No.
Like so right now the zero coordinate is the highest up.
Yes.
So like for mine the zero coordinate is like the lowest down.
Oh, yeah. It's more that you'd start here.
Yeah.
It's more like this. I want to be careful saying it's completely flipped. Because you have problems at the 240 and 300 if you say that. That won't exactly work for you. If you flip it 180 degrees like that, it's more that it got shifted over. So that's why I'm like being, you're thinking only of this one, which would be right, but then you get to the 60 degrees and yeah. No, it would be, you're right. You're right, it would be flipped. Yep. Yeah, it would be flipped. It's just gosh, that's a little confusing. Anyway. I continue rotating around. Hopefully this doesn't come as any surprise to anybody here. Now we're not going to do anything crazy where we have like 3 substituents or anything like that, where we have to really work harder at figuring out which one's going to be more stable using Gauss tables or anything like that. There are tables of the instability of the Gauss interactions. Same thing with the axial interactions for more difficult problems. She hasn't included those, so we're not going to either. Okay, so we're gonna. She's moving into chirality on Friday, and so I think that's as far as this problem goes. Any questions on this? Okay. I want to save one of the Newmans there because it could be a real pain trying to redraw that in the middle of lecture. All right, problems like this, I wanted to hit up, let's do A here. Students at this point usually do a very good job on these problems. The problem usually becomes counting carbons. I like to make mistakes counting carbons on this, and so keep that in mind as you're doing these problems. Make sure you sit there and count the carbons on your Newman projection. It can be embarrassing when you're in recitation trying to teach and you make a mistake on that. So we're doing A here. I'm doing bond line formula first. Hopefully this comes as no shock. 2-methylbutane. You have a 4-carbon chain with a 2-methyl group coming off of the 1 point. Now, again, just to hit up what we're going to be talking about Friday, there's actually 4 different things coming off of that second carbon. And this is actually chiral. This will actually have some different chemistries here, whether it's a wedge or a dash. Okay. For now, we're going to ignore that. Well, or sorry, I'm incorrect. My bad, because the methyl groups are the same. So here, we bring in our staggered. We're looking down this carbon here. No problems there, right? There's no way to make it truly anti. You're going to have some Gauss interaction.
So would it get the same energy level if you did split the C3 methyl group down where the, like on the bottom
Yeah,
spot. Okay.
yep. There would be two right answers there. All right, B here is an example of one of the mistakes I made in recitation on Tuesday. 3-methylpentane here. Is like this. You want to count carbons and make sure that you're doing the right. So I have an ethyl group here coming off that C. Sorry here. I'm making mistakes left and right today. Since we're setting down the C2, C3 carbon, I apologize, not the C3, C4. You end up with an ethyl group on that back carbon, and you end up with a methyl group. And you want to make sure that the ethyl and methyl, well, the methyl group from the C2 carbon and the ethyl group from the C3 carbon are anti to one another. Counting carbons for the pentane here, 1, 2, 3, 4, 5, with that methyl group coming off the third carbon. I would recommend slowing down during the moon projections, particularly if you get some long carbon chains like beyond pentane, to make sure you don't make a mistake on that. Any questions on that? I'm going to go and do some more problems here. So this is going to be at the end of lecture. We start doing this cis and trans stuff. I'm going to start with a basic wedge dash off of cyclohexane here. We're going to start with A here. So the problem asks to draw two chair conformations for the next molecules and underline the most stable one. So this problem here, what you need to do is first start off, I would start off with a basic hexane here, put in your wedge and dashes, then convert it to the chair conformation, and then draw the other chair conformation. So what does cis mean? They're all on the same side. Does that mean it's particularly wedge or dash? No. It can be either right now. Later on, we're gonna start including like R and S, and then you can start actually isolating which way they'll go. But because I like wedges, if you did dashes, that's fine. Oops, and it's 1 and 4. So that means 1, 2, 3, 4, with the 1 getting the tert group. And again, at this point, we should all recognize that this is going to be T-butyl, right? Everyone got that? So if you don't recall that, you have the 4 carbons here making the butyl group, and it ends with a T, so you get butyl or tert. Now comes my fun talk about how to do, let's call this just doing the axial positions here. I'm going to do equatorial in a minute. You need to know whether equatorial is up and down at each of these carbons. You know whether axial is up or down at each of these carbons. I think a good way to go is to start with the ends. If you have a vertex here and you see how it's going up above a horizontal line, that means that the up position is, or axial is up. Same thing here. That axial position is, or the vertex there is pointed up. when you bring up the two lines, and that makes it up. Same thing here. You know, so over here, the vertex is kind of pointing down and to the left, so it makes the axial down, and whoa there, axial down. Now, this method doesn't work for everybody, but if you can get the tips right, now I'm numbering this clockwise, numbering this, I guess, lettering this. I like to put my substituents in the most left or most right position if given the opportunity. Does that mean you have to? No, there's a lot of right answers when it comes to this stuff. I'm giving you my way of doing it. Now, if you know what the axial position is for A, if you draw a triangle in the middle of a hexagon like this, you'll notice that A, C, and E here will share the axial positions in the same direction. B, D, and F also share it in the same direction, but it's the opposite way. This isn't in any textbook. This is my method of doing it. If this doesn't work for you, completely ignore it. But for a lot of students, this starts to help because now you only need to memorize one axial position and you can get the rest of them right. Okay? Now remember, axials are either up or down and a vertical line. Equatorial positions are kind of put in at a diagonal. And equatorial positions are going to go away from this vertical line on the cyclohexane. They're going to go away from it. Let's start with D here. Since the x position is down, what's to make the equatorial position? Up and away from this vertical line that I drew. Imagine that's straight here. E here, the x position is up. That makes the equatorial position down and away from that vertical line. Away, 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 and away. Before the exam, you should be able to do this in your sleep. So I don't know, I'm hoping that will help. Tuesday, they were having a lot of issues with this. I'm hoping Wednesday's lecture, and I'm hoping we're not putting you guys to sleep here. But for those of you in the crowd that are having issues with that, I hope that really helps. I can guarantee you, you are not alone. We're going to see a lot of interesting cyclohexanes. In particular, if I see this on my problem, something like this, I will probably, you always grade it all wrong. Okay, it tells me that you don't understand what axial positions are, right, for D here. So make sure you clearly label which one's axial, which one's equatorial. If you're really having issues with it, put an AX next to it. If you can't somehow draw it straight up or down. Make sure we clearly understand what you're talking about. Okay, so now we're getting to the actual meat and potatoes. I'm going to delete all this. That rule set also works with the chair flip or the confirmation change if you go to this guy. So here, I can't tell you right now, right away, whether the tert-butyl group or the methyl group coming off the cyclohexane are axial or equatorial. I know they're going up. They're coming out of the sheet of paper here. Now, when we go from this figure here on the left to the one on the right, we're flipping the molecule 90 degrees. So instead of looking down at it, we're looking at it from the side. Okay, instead of looking down at it, we're looking at it from the side. So now up will be up on the sheet of paper. Now on A here, up happens to be axial, which means the tert-butyl group is what? Axial or equatorial? Yeah, it's going to be axial. D here, whoa. Yeah, I've been talking a little bit too much, I guess. D here, the methyl group is axial or equatorial? Why is it equatorial? Right. The equatorial position, or the up position is equatorial, so therefore this is equatorial. Notice how I'm saying that. I'm not saying the equatorial position is up. I'm saying the up position is equatorial. I'm basing my thinking on, okay, I need this to be up and in the same direction as my terp-butyl group. Now, I'm going to draw something out here. I want you to tell me if I'm right or wrong and why. I always like putting up wrong answers or commonly wrong answers for students and addressing them. Is that a conformational change? What is this technically? You can describe it in your own words. It's fine. I call it a ring flip. So like, think about a student cooking a pancake and they flip it over. It's the same molecule flipped over 180 degrees, and they think that's a conformational change. That's not what a conformational change is. Okay? A conformational change twists and turns carbon bonds. But the story will remain the same in terms that the substituents are still going to be in the same direction and they're still going to be pointed up. Now, when I'm drawing the chair or the conformational change here, the way I like to think of it is these carbons tend to be locked in place. This group moves down, this group moves up. That actually gets you through the twist boat, or the half chair, the twist boat, the boat conformations. If you walk through the cyclohexane conformational change, that is what is happening. Okay? One end will flip up, down, one will flip up. I like to think of it as an envelope with two open ends. So one's pointed down, and then so you see this this block here stay in place. Now this methyl group here is now an axial. They switch from axial to equatorial, equatorial to axial. Which one's gonna be more stable? Oh, I messed up here. It's supposed to be an ethyl group, my bad. Let me fix that really quick. It doesn't change the overall story that much. This would ding me a point on the exam here. Which one's more stable, left or right? Why? Yes. Okay, so she did go through some A values, which is the difference in energy between something being the equatorial position and something being the axial position. This includes some of the Gauss interactions that you might see. Students sometimes think that if you have two methyl groups next to each other that are equatorial, they'll have more Gauss interaction. That's technically incorrect because in the axial, there's more Gauss interactions if you look down all the carbons. So we tend to ignore that because it gets really confusing. So we're just saying put the more bulky group in the axial position or more of, or in the equatorial position. Same thing with just more substituents, make sure more of them are in the equatorial position. We're gonna make sure the groups tend to be fairly, if you have multiple substituents, they're all gonna be methyls or ethyls. We're not gonna do anything insane. But understand the problems will lead there if you continue down the organic chemistry path. The time is now 9:05. It's a quiz time. So please email me any questions or in the chat box once you're done with the quiz. Good luck and have fun, I guess.